Suppose you have a domain that's closed and bounded. Okay, you're familiar with open intervals. Now let's do a closed and bounded interval as your domain. So first, what do you mean by closed? Well, in this context, you also include the endpoints. Okay, so before you were familiar with the open interval AB. Okay, in the domain. Now we will include points A and B. Okay, so uh, this is now closed and it's bounded because we have an upper bound B and a lower bound A, in this case in the domain. So for example, you have a function like this. Okay, now it's defined between 2 points A and B, which includes A and B in the domain. Okay, so let's examine the case when your domain is a closed and bounded interval, and we'll try to find optimizers within that closed and bounded interval. Now, a very important theorem, Weierstrass theorem, says that if you have a continuous function in such a closed and bounded interval as a domain, then it has both a maximum and minimum on that interval. So just to formally state it, a continuous function defined on a closed and bounded interval has a minimum and a maximum on the interval. Okay, so you're guaranteed that a minimum and a maximum exist on that interval. So let's go to an example. So suppose you have this function f of x equals 1/3 x cubed plus 2x squared minus 5x plus 3. Okay, and suppose this function is existing in the domain -4, 3, which is a closed and bounded interval. Okay, so it exists in this domain -4 to 3. Now notice this is a closed and bounded interval because it includes -4, it includes the endpoint 3. Okay, and we know that the function f is differentiable and therefore it is continuous over this domain. So we can invoke the Weierstrass theorem, and the Weierstrass theorem says that the function f over here has a maximizer and a minimizer, okay, that exist in this interval. So what does the Weierstrass theorem say? So the maximizer or the minimizer can either be in the interior of the domain -4, 3, where it is a stationary point. So let's go there. So how do we find the stationary points? Well, we just get the derivative of this function f of x. So f prime x here is just bring down the exponent. So it's just x squared plus 4x minus 5. Okay, so it's here. And then further solving that, you have x plus 5 times x minus 1. Okay, then you set this derivative equal to 0 to find the stationary points. Great. Okay, so when will this be equal to 0? When will this derivative be equal to 0? Well, it will be equal to 0 when either this expression or this expression is equal to 0. So this expression will be equal to 0 when x equals to -5, right? So -5 plus 5 is 0. This will be 0. This expression will be 0 when x equals to 1. So therefore, you have two stationary points, x equals to -5 and x equals to 1. Great. But one of the stationary points, x star equals to -5, is outside this domain, this closed and bounded interval. So it's less than -4. So we disregard that, okay, because the function only exists in the closed and bounded domain here. So we have one candidate stationary point, x equals to 1. And there are no other critical points since you have the derivative existing everywhere inside that domain, -4, 3. There are no other points there where there's a kink. Okay, so the derivative, or yeah, the derivative exists. Okay, so there are no kinks in negative 4 3 in that interval. So okay, so we have interior points in the interval negative 4 3, which is a stationary point that could be the source of the optimizer, or the maximizer or minimizer. The theorem also says that you have to evaluate at the endpoints, okay, to determine whether it's a maximizer or minimizer. So the endpoints are negative 4, this is the lower bound, and positive 3, which is the upper bound. Okay, so these are the endpoints. You have to evaluate the function there to see if those points are maximizers and or minimizers. Okay, so here's the function again. And we have the three candidate points: x equals to 1, x equals to negative 4, and x equals to 3. So recall that negative 4 and 3 over here are the endpoints, and this one is a stationary point. Great. So what do we do? Well, we just insert this values of x's in the function to determine whether it's a maximizer or minimizer. Okay, so if we substitute 1 to the function, so we have 1/3 times 1 cubed plus 2 times 1 squared minus 5 times 1 plus 3. If you do the calculation, this is equal to 1/3. Now, if you insert negative 4 here, you have 1/3 times negative 4 raised to 3 plus 2 times negative 4 raised to 2 minus 5 times negative 4 plus 3, which is 101 over 3. So roughly around 33 to 34. Okay. And then if you substitute the point x equals to 3, so you have 1/3 times 3 cubed plus 2 times 3 squared minus 5 times 3 plus 3. This will be equal to 15. Okay? So this is roughly around 33.8. Okay? I may be wrong, but it's just an approximation. So notice that this function over here attains its lowest value at 1/3. Okay, at x equals to 1, which gives a value of 1/3. Okay, that's a minimum. And the highest value is attained at the point negative 4, x equals to negative 4, which gives around 33.8. Okay, the other one just gives 15. So, see, indeed, we have a minimum and a maximum. Okay, so where does the minimum occur? Well, the minimum occurs at the interior point, okay, at 1, which is an interior point, and which is also a stationary point. And the maximum occurs at negative 4, which is an endpoint, okay? An endpoint in the closed and bounded interval negative 4, 3. Okay? So the maximum occurs at the endpoint, the minimum occurs at the interior point, which is a stationary point. So indeed, if you look at the graph of the function, this is the graph of the function in the orange line. Indeed, the maximum occurs at the endpoint negative 4. Okay, x equals to negative 4 is where the value of the function is highest. Now you know that negative 4 is an endpoint. Okay, and the minimum occurs at x equals to 1. Okay, which is an interior point. Interior meaning it's inside the closed and bounded interval negative 4 3. Now, moreover, that interior point here is a stationary point. You have the tangent line horizontal over here. Great. So the Weierstrass theorem says that if the function is continuous um, in a closed and bounded interval, okay, so endpoints are included, you are guaranteed to have a maximum and a minimum. Okay, so the maximum can or minimum can occur either at the endpoints or at the interior. Okay, so at the interior, it can either be a stationary point or a point where there's a kink, for example. Great. So now let's go to concave and convex functions. Okay, so consider this graph over here. Okay, so this is your function f of x, which is this kind of like a purple line. Okay, this purple curve over here. So intuitively, a function f is concave on an interval in the domain if and only if, okay, if and only if the line segment joining any 2 points on the graph f, okay, so uh, 2 points, call this, let's change the color. So this is 1 point on the graph, this point on another graph, and draw the line segment that connects the two. Okay, great, this one. So if such all the line segments are below the graph, on or below the graph, then that function is concave. Another line segment would be joining, for example, these 2 points. Okay, this one. Notice that this line segment is below the graph. Okay, okay, and another one would be this, and say this. Join that line. Join those points with the line. Notice that this line segment is also below the graph. Okay, so if you have a function and you see the graph, pick any arbitrarily pick any 2 points and then connect the 2 points by a line. And if those all those points by picking two, I mean all those lines by picking 2 points lies below the graph or on the graph, then this function is concave. Well, um, the way I would think of it also is that if it looks like a cave, then it's concave. But that's just um, a tongue-in-cheek description of a concave function. Okay. On the other hand, a function is convex when you have 2 points and then join those 2 points by a line segment, and you find that for all those 2 points, that all possible 2 points that you choose. Okay, so this is one, this is another. Okay, pardon the line, it's not that straight, but you get the idea. If all those line segments lie on or above the graph, in this case it's above the graph. Okay, there's, how about this 2 points extreme over here? Okay, so it lies above the graph, then this function is a concave function, convex function. Okay, so if all the line segments lie above or on the graph, then this function is a convex function. Now, if all line segments, by choosing arbitrarily any 2 points, okay, so all line segments are below the graph, not on the graph. Okay, so if they are below the graph, all of them, there are no points that are on the graph. If all such line segments joining 2 points in the function are below the graph, then it is a strictly concave function. So here's an example of a function that's concave but not strictly concave. Okay, why? Because 2 points here on the graph, oops, 2 points in the graph over here are on the line, okay, are on the function or on the graph. Okay, so C and D, if you join the line here, it's on the graph. Okay, so if you don't find points where uh, the line segment is on the graph, but all the line segments are below the graph, then it's a strictly concave function. But this function over here is a concave function, but not strictly concave. So another point would be this and this. If you join that, it will still be on the graph, okay, on the line on the graph. Uh, this is not a strictly concave function. So analogously, if you have a function and the graph looks like this one, where any 2 points lie above the graph, so you won't find any points that are on the graph. okay, all 2 points are above the graph, then this is a strictly convex function. Okay, so here there are no flat parts, so all line segments joining 2 points are above the graph. Okay, so this is a strictly convex function. Now this is an example of a function that's convex but not strictly convex. Okay, so again you have a flat part over here where when you join this 2 point C and D, the line segment is on the graph. Okay, so the definition of a convex function is that 2 points are either above the graph or on the graph. Okay, a strictly convex function is all line segments joining 2 points are above the graph. Okay, so all in this case, if you take 2 points like this one, it's on the graph, so it's not strictly convex. Again, to reiterate, if the function is strictly convex, okay, so something like this, any 2 points joining any line segment joining 2 points is above the graph. All of them are above the graph. Okay, in short, there are no flat parts. Okay, here we have flat parts over here, so if you join 2 points in those flat parts, it's on the graph. Okay, but elsewhere, if you join 2 points, it's above the graph. So if you have such flat parts, it's not strictly convex, but it's convex. So there are functions that are neither concave nor convex. So take this function x cubed over here with this graph. So notice that when you join 2 points, for example here and here, this lies above the graph. Okay, but if you join 2 points in this segment, uh, this and this is below the graph. Great. So there are parts where uh, the line segment is above the graph. There are parts when the line segment is below the graph. So this doesn't satisfy the definition of convexity nor concavity. So this function is neither concave nor convex. But there are functions like a linear function, this line over here, that's both concave and convex. Okay, so what's the definition of the of concavity again? When you join 2 points, it's either on the line or below the line. Okay, below the graph, that's concavity. If it's convex, it's on the line, the line segments are on the line or above the graph. Okay, on the graph or above the graph. So here in this case, because every 2 points here is on the graph, okay, so join these 2 points, say CED, it's still on the graph. Join another 2 point, say EF, the line connecting them is still on the graph. Then this satisfies the definition of both concavity and convexity. So therefore, this is a function that is both concave and convex. So alternatively, we can think of convexity and concavity in the following way. So suppose you have a concave function like this function over here. It's a concave function. Now notice that uh, at any point, the tangent line lies above the graph. Okay, so here in this point, say this is x1, the tangent line is above the graph. At this point x2, again, the tangent line is above the graph. Pick another point, say x3, over here, the tangent point is above the graph. So a function is concave if and only if the tangent to its graph at any point on the graph lies on or above the graph. Okay, so analogously, a convex function like the one found here, pick any point. Okay, so let's start with this one because this is already illustrated. Let's start at x1. The tangent line at x1 is below the graph. At x2, at this point x2, it's still below the graph. And here x3, tangent line is also below the graph. Okay, so a function is convex if and only if the tangent to its graph at any point on the graph lies on or below the said graph. Okay, so you can also think of concavity and convexity using the slopes, using the tangent lines at, at different points of the function. Now let's go to the first derivative test for concavity. Okay, so here we have three relevant points. So we have the point A, oops, we have the point big A here, we have A, we have B, we have B, and C. Okay, so BB over here, that uh, term BB refers to this height from big B to small b. Okay, so this height is BB. Or equivalently, we could trace it here. Okay, so this height, okay, this height is BB. Let's just put it here, BB. Okay, so BB, that height is equal to f of A. What's f of A? This is the point A. So f of A is where it touches the graph. The value touches the graph here. So this is f of A, okay, which is this height. This height is f of A. Great. Plus BC. So BC is this height over here. So this height from f of A to BB, from f of A to this point over here is BC. Okay, so I'm just decomposing this height to this height BB to f of A, which is this height over here, plus BC. Okay, great. I hope you're following. Okay, so we have BB over here, we have FA over here. Now, notice this. What is BC? BC is this height. Okay, and this height is the rise. Okay, and B minus A over here is the run. So therefore, the slope of this tangent line, okay, which is f prime A, okay, this is the slope of the tangent line that just touches A at point A, is equal to the rise. The rise is BC, okay, and the run is this distance. Okay, so this distance is just B minus A. Okay? So this whole distance is B. You take out the distance A over here. This distance over here is B minus A. Great. So just moving things around, we have F prime A times B minus A is equal to BC. Great. So I hope you're still following. So therefore, we substitute this BC, which is this value, to here. Okay? So BB is equal to F of A plus F prime A times B minus A. Good? Great. Okay? So by concavity, we have that F of B, okay, which is this one. Let's pick another color because this is getting kind of messy. Um, Suppose we have green. Okay, f of b is where the function is valued at point B. So, okay, this is f of b. Great. So it's the value of the function at B. So obviously, as you can see here, f of b, this distance, is less than BB. So by concavity, that's always true. So FB is less than or equal to this height BB. Okay, great. But we know that BB is just this value over here. So we substituted this one for BB. And when we move things around, when we put f of a to the left-hand side, we have fb minus fa is less than or equal to f prime a times b minus a. Okay? So a similar result can be derived for convexity. So therefore, a differentiable function f is concave on an interval I, okay, if and only if every pair of points AB in that interval I, okay, like what we saw in the last graph before, we have that FB minus FA is less than or equal to F prime A times B minus A. Great. So when your function is concave, this is always true. So on the other hand, if a differentiable function f is strictly concave, okay, strictly concave on an interval I, if and only if we pick 2 points A and B, on that interval, we have that it's similar, FB minus FA, but this is now strictly less than F prime A times B minus A. Okay? So if it's concave, it can be equal, but if it's strictly concave, this expression is always less than F prime A times B minus A. Great. So similar and analogous, a differentiable function f is convex when we have 2 points A and B on an interval where FB minus FA now is greater or equal to F prime A times B minus A. When it's concave, it's less than or equal. So it's convex if this one is greater than greater than or equal to this expression over here. So again, similar to what we had earlier, a differentiable function f is strictly convex on an interval I, where you pick any points A and B in that interval. We have fb minus fa is strictly greater than f prime a times b minus a. Okay, so if you pick any 2 points A and B in that interval and this holds, it's strictly convex. Now consider the graph on the right, okay? So you know that this graph is concave. Okay? Now, suppose we have 2 points A and B here, and there's an interval A and B here. Now, as you go from A to B, what do you notice? At this point A, the tangent line is has a very, very positive slope. And if you move further, this will still be positive, but it's flatter, so it's a smaller positive number until you get to this part where it's flat. So the slope of the tangent line is 0. Then as you move further, the slope of the tangent line becomes negative now. And as you move closer and closer to B, the slope of the tangent line is a steeper negative. Okay? So it's a bigger negative number. So you start with something that's highly positive, okay? Then you go to 0, decrease to 0, then you go to negative and very, very negative. So the slope, the tangent line, decreases from positive to negative as x moves from A to B. This is equivalent to saying that the second derivative is less than or equal to 0 for all points x in this interval A to B. Okay? So that's for a concave function. Okay? So for convex function, you derive a similar result. Okay? So suppose you have an interval A, B over here. So as you move from A to B, okay, you start out with a very, very negative slope. And then as you move further out, it's still negative, but it's flatter. So it's a smaller negative number. Then as you go here, the slope becomes 0. So negative, 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 then 0. Then as you move further out, it becomes positive. The slope becomes positive. Moving further out, the slope becomes a more positive number, the slope of the tangent line. So this is equivalent to saying that the second derivative f prime of x is greater or equal to 0 for all x in the interval a b. Okay, so again, just keep in mind that for concave functions such as this, the second derivative uh, is less than or equal to 0 for all x in the interval a b. On the other hand, if it's convex, then the second derivative is positive or 0, greater or equal to 0 for all x in this interval a b. Now we have the second derivative test for concavity, which just formalizes the graph that we had in the previous slide. Okay, so this is the theorem. If we have f as a continuous function with continuous second derivatives, okay, on an interval ab, then f is concave on that interval if and only if the second derivative is less than or equal to 0 on ab. Okay, so the example in the previous slide illustrates what this theorem means. Now, if the second derivative is strictly less than 0, or it's always negative for all x in that interval, okay, the second derivative is always 0 for all x, then f is strictly concave, okay, on a and b. So in this case over here, for concavity, the second derivative can be equal to 0. Okay. It's strictly concave when the second derivative is always negative for all x on AB. Analogously, if f has continuous second derivatives on an interval AB, then f is convex on AB on that interval if and only if the second derivative is non-negative. It's either positive or 0, okay, on AB. Now, if the second derivative is positive for all possible values of x in the interval AB, then f is strictly convex on that interval. Okay, so like the definition, like the illustration that we had, the second derivative is positive. So it starts from a very negative slope, then it goes to 0, then it goes positive. So the rate of change of the slope is increasing. Okay, slope of the tangent line, I mean. So when that happens, then you have a concave function. Sorry, I mean a convex function. So if you have the rate of change is positive, it starts from a negative slope of the tangent line, goes to 0 and goes up to positive, then it's a convex function. If it starts from uh, a very positive slope of the tangent line, and so the second derivative is less than 0, it means that the rate of increase is decreasing. So you start from a very positive slope, go to 0, and then end up with a negative slope as you go from left to right, then it's a concave function. So here is an example. Suppose you have this function square root of x, or x raised to 1/2, and the domain is for all positive values of x. Okay. So when you get the first derivative, it's 1/2 x to the negative 1/2. Okay. And if you get the second derivative, so you bring this exponent over here and multiply it here. So that's negative 1/4 x. Negative 1/2 minus 1 is negative 3/2. Okay, so that's the second derivative. Now notice that this is equal to negative 1 over 4 times 1x 3/2. Okay, so for every value of x that's positive in this domain, okay, this one is always positive. So therefore, the sign of the second derivative depends on the negative 1/4. So it's always negative, okay? Because this part over here is always positive. You multiply a positive by a negative number, the second derivative, therefore this whole expression is negative. And this is true for all values of x that's greater than 0, that's positive. So therefore, by the theorem, okay, so by the theorem, you have your second derivative less than 0 for any x in the interval. In this case, the interval is 0, infinity. Okay, then therefore this satisfies the definition of strict concavity. So therefore, the function f of x over here is a strictly concave function on the interval or on the domain 0 to infinity. Okay, good. So here we have a linear function, f of x equals to x. Now notice that the first derivative is equal to 1, a constant, so therefore the second derivative equals to 0. Okay? So this is true for all values of x in the real number line. So even negative infinity to infinity. Okay? So whether you go here or you go here, it's the second derivative is equal to 0. Great. So it satisfies both the definition of concavity and convexity, because what does the definition of concavity means? Say it's that the second derivative should be less than or equal to 0. So in this case, it's equal to 0, so it satisfies the definition of concavity. And it also satisfies the definition of convexity, because it requires that the second derivative f prime prime x should be greater or equal to 0. Since this second derivative equals to 0, then it also satisfies the definition of convexity. So therefore, this function is both concave and convex on the domain, the real number line. So finally, we have this example. So we have the natural exponential function e of x as our function. Okay, so this is the graph of it. And when we get the first derivative, it's the function itself, e of x. When we get the second derivative, it's the function itself, e of x. Now notice that the domain here is the real number line, so negative infinity to positive infinity. So if x is negative, for example, um, e of a negative number, okay? So if you have negative x over here, this is just equal to 1 over e of x, okay? This is still positive, okay? So if x is a positive number, this value e of x is positive. So no matter if x is negative or positive, the function e of x, or this derivative, second derivative e of x, is always positive. So it's greater than 0 for all possible values of x, be it negative or positive. Okay, so it satisfies the definition of strict convexity, because strict convexity requires that the second derivative be positive for all possible values of x in the interval. Now, in this case, the interval is negative infinity to infinity. Okay, so that's the domain. So in this case, whether x is negative or positive, the second derivative is always positive. So therefore, this function is strictly convex. Okay, because it satisfies the definition of strict convexity. So here are two theorems that characterizes the optimizers of concave and convex functions. So the proof of the theorems are in the now. So here, the theorem says that if f is a differentiable function, if it's differentiable, then it has no kinks. Okay, so f is a differentiable function on an open interval I, and let a particular point there, call it x star, be an element of I. Okay, so if that function f is concave on that interval, on that domain, okay, then x star is a local maximizer of f if and only if x star is a stationary point of f. Okay, so the proof is in the now, but I'll just give the intuition here. So suppose you have a concave function over here, and you have this interval I, okay? So from here to here, this is I. uh, open interval, so you don't include the endpoints. So this is a concave function. Okay. So let's get a particular point x star here. This theorem says that x star is a local maximizer of f if and only if x star is a stationary point. So what is a stationary point? Well, it's the point where the slope of the tangent line is horizontal. Okay? So this is where f prime x star is equal to 0. So the slope of the tangent line at x star is equal to 0. So obviously, since this is a concave function, you start with, if as you go from left to right, you start with a positive slope, and then you go to 0, and then as you go further right, the slope becomes negative. It means that the function is increasing, and therefore, at the stationary point where the slope is horizontal, that attains the highest possible value of the function, and then it decreases uh, as you go to the right. Okay, so at that stationary point x star, the value of the function is maximized. So therefore, x star is a local maximizer at that stationary point x star. Okay, so on the other hand, if you have a convex function like this, okay, and you have the interval, uh, this interval over here, okay, call that I, and you have an x star, then x star is a local minimizer if and only if x star is a stationary point. So a stationary point means that the slope of the tangent line at x star is equal to 0. Okay, that's a local minimizer um, at this interval I. So obviously, because this is a convex function, you start out with a negative slope over here, so the function over here is decreasing. Okay, as you go from left to right, then it becomes horizontal, becomes 0. Then the function is increasing. So therefore, the function attains its minimum value at x star, okay, where x star, the slope of the tangent line of the at x star is horizontal. So that's the intuition of these two theorems over here. Now, as you notice, when we tried to sketch the intuition of the previous two theorems over there on the previous slide, you notice that that local minimum or maximum is also a global minimizer or maximizer. Okay, so I mean the local maximizer or minimizer is also a global maximizer or minimizer. So just to reiterate, these are two theorems. So every local maximizer of a function that is concave on an open interval I is a global maximizer. So every local minimizer of a function that is convex on an open interval I is a global minimizer. So again, since your function is concave, okay, let's illustrate. So suppose this is your interval I for which this function exists. Okay, so suppose this is I, the domain, okay, and then we know that the local maximizer here is at this point where at this point x star is where the slope of the tangent line is equal to 0, meaning that x star is a stationary point. Great. But since this function is concave, like I said in the previous slide, all the slopes of the tangent line here starts with a very positive number, and then it goes to 0 as you move from left to right, and then it's negative. So therefore, the function is increasing and increasing to the left of x star, and then decreasing and decreasing everywhere to the right of x star. So therefore, not only is this a local maximizer at x star, not only is x star a local maximizer, it is also a global maximizer in this domain, because since the function is concave, you to the left of x star, the function is increasing. To the right of x star, the function is decreasing. So therefore, x star is also a global maximizer, not just a local maximizer. The same thing for convex functions over here. Suppose you have this domain, oh, sorry about this one. Suppose you have the domain over here from this to this. This is your domain I, this interval I. And we saw from the theorem a while ago that this is a local minimizer, x star, where x star is a stationary point, meaning the slope of the tangent line at x star is equal to 0. Great. So since this is a convex function, we have that if you go from left to right, the function is decreasing, okay, initially. So the function here, the tangent lines are negative, so the function is decreasing, 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 until you go to the point x star where it's 0, then it starts to increase, okay? So you start decreasing and decreasing in this part of the function until you reach x star, and then the function continues to increase as you move away from x star. So therefore, x star here is also a global minimizer, okay, in this domain over here. So that's the beauty of concave and convex function, is that concave functions, once you find the local maximizer, that is also a global maximizer. In convex functions, if you find the local minimizer, that's also a global minimizer. So those are the good properties of concave and convex functions.